Okay, so we're starting chapter 2 now. Chapter 2 is significantly shorter than chapter 1. We only cover 3 sections in this chapter, and we actually only cover part of section 2.3. We're not going to be covering Kramer's rule. Now, chapter 2, the focus is all on determinants. In chapter 1, we introduced the definition of a determinant for a 2 by 2 matrix. And I had mentioned in that section that the determinant is something that we can do on any square matrix, any n by n matrix. But we were leaving it to chapter 2 to give a definition for that. So we're going to do that now. And I will preface this section with this. The determinant is going to be defined in a way that seems very bizarre. I don't know if I'd say random necessarily, but it's going to seem like an unusual thing to do with the entries of a matrix. And we're not going to get a clear picture of what the determinant is, why it actually arises naturally in this chapter. But we will at the end of chapter 3. I'm going to add a video that's going to tie together some of the concepts from chapters 1 through 3 once we get that far. And we're going to see that the determinant has a very, very important geometric interpretation that your book doesn't really cover very well. So if you're going through this section with me and you're thinking the determinant thing doesn't seem to make a whole lot of sense, I get how to do it, but why are we doing it? What does it mean? Just hang on to that thought. We'll put some clarity into this once we get past chapter 3. Anyways, back to what we were talking about. So a little review. The determinant of a 2 by 2 matrix is the difference, this should be an equals right here, it's the difference between the product of the main diagonal entries and the product of the other two entries, AD minus BC. And we used the 2 by 2 determinant to find inverses. It came up in a formula for finding the inverse of a 2 by 2 invertible matrix. Okay, now our goal here is to take this idea and generalize it to any square matrix. So what we're going to do is let A be some n by n matrix, and we're going to define some terminology. The first thing we're going to define is what's called the minor of entry Aij. So any entry in that matrix has what's called a minor associated with it. And what it is it's the determinant of the submatrix that results from deleting the column and row that entry appears in. So we'll illustrate that with an example in a moment. The cofactor of that same entry Aij, which we use this notation for. Notice minors are denoted Mij, where Ij is the same position as that entry. Cofactors have a capital C in their notation. The cofactor of an entry is either going to be equal to the minor or the opposite of that minor, so plus or minus. And the way we determine whether it's the minor or its opposite is this little factor right here, -1 to the power of I plus j, where again I is the row and j is the column in which that entry appears. Okay, so it's a little tricky kind of wrapping your mind around that without seeing an example. Let's do an example. We want to find the 1,1 minor for this 3 by 3 matrix and the 3,2 cofactor for this 3 by 3 matrix. So for the 1,1 entry, which is this entry right here, 3, since it appears in the first row and the first column of this matrix, we would imagine deleting that row and that column so that the minor for that entry is the determinant of the 2 by 2 matrix that remains after deleting that row and column. 4, 6, 3, -5. Okay, so you can see where that came from right here. And then because this is now a 2 by 2 determinant, which we've defined, we can evaluate this directly. 4 times -5 minus 6 times 3. That's -20 minus 18, which would be -38. Okay, Now for the cofactor, and it's a cofactor for a different entry. This time it's the 3, 2 cofactor. I find the entry in the third row, second column. So third row, second column, that's this 3 right here, okay? So the cofactor associated with this entry is going to be the, it's going to come from deleting the column and row because we need the minor first. So actually, let's write this. C32 is equal to -1 to the power of I plus j, where I is 3, j is 2. 3 plus 2 times the 3, 2 minor for that entry. Okay, so 3 plus 2 is 5, -1 to the 5th power is -1, so I'm going to say minus, and then the 3, 2 minor is going to be the determinant that we get from deleting that row and that column, 3, 0, 2, 6. Those are the entries that remain. 2, 6. This is equal to negative 3 times 6 minus 2 times 0, which equals negative 18. Okay? Now, in practice, we oftentimes don't use this formula directly. Because if you notice, again, the -1 raised to this power here is only ever going to become a positive or a -1. It's going to be positive if I plus j is even, negative if I plus j is odd. Now, if you were to go into some kind of general matrix like this and look at the 1, 1 entry, 1 plus 1 is 2, an even number, that would give me a positive factor here. The 1, 2 entry, 1 plus 2 is negative, so that is odd. It gives me 3, so -1 to the 3rd power would be -1. And we're going to get this alternating pattern, which is easy enough to see, of pluses and minuses, creating sort of this grid that we can use as sort of a guide. Now, the reason it's helpful to have this grid is because when we're evaluating determinants of larger square matrices, we're going to be computing several cofactors all at once. So rather than do this direct formula every single time, we can just think of this alternating pattern of pluses and minuses. Okay, so now let's talk about how we use cofactors to find the determinant of some n by n matrix. So the way that we define the determinant, and there's actually several different but equivalent ways of defining the determinant of a square matrix. We're going to use cofactor expansion here. Cofactor expansion is what happens when you take a matrix and you select either a row or a column, any row or any column, and then you evaluate this expression right here. So for example, if we want to do cofactor expansion along the jth column of our matrix A, then what we do is we find that jth column, let's say it's this one right here, and we multiply each entry in that column to the cofactor that's associated with that entry. And then we do that for every single entry in that column and add the results. Okay, and remember, because whether we choose a column or a row, we have this alternating pattern of pluses and minuses. We have to be careful to keep track of those as we do this expansion. The same thing we can do the same thing performing cofactor expansion along some row. So if this is the ith row of a matrix right here, I can do the same thing. Select each entry in that row, multiply each entry to the cofactor associated with that entry, and then sum all the results. That's what this is telling me. Okay, now we're not going to prove this. It takes us a little bit further outside of the scope of what we want to do here, but there's a remarkable fact about this. Regardless of the row or column that you choose to expand upon when evaluating a determinant, you will always get the same value. It seems very bizarre that would happen, but it always comes out to the same thing. We're going to illustrate that in an example. So, and then one final thing. Because a 1 by 1 matrix is technically square, we can take determinants of those, but we simply say that the determinant of a 1 by 1 matrix is that entry. So there's not really much to talk about there. All right. So here's another example of a 3 by 3 matrix, and we're going to evaluate the determinant of this matrix using first some column, and then second some row. And I'm going to show with that we get the same thing regardless of which direction we go. So let me start by expanding this along, let's say, the third column. Okay, now if you remember that grid, that plus minus grid that we talked about, we had plus, minus, plus. And we always get alternating pluses and minuses whether we go along a row or a column. So this one is associated with a plus. That means I'm going to have plus, minus, plus. That's the pattern that we want to use. Plus simply means that we don't change the sign of the minor when we calculate it. Minus means we do change the sign. So if I'm going to do cofactor expansion along this third row, so I'm going to say third row, or column, sorry, it's a column. Then what I do is I start with this first entry, 1, and it's because this is associated with a plus, I don't change its sign, and then I multiply it by the 2 by 2 determinant that I would get by deleting this row and this column. 0, 2, 1, negative 5. Okay? Minus, because in the next case we go from plus to minus, 0 times the determinant that I would get by deleting this row, this column. That's 2, negative 4, 1, negative 5. Okay? Now because there's a 0 here, I'm not actually going to evaluate this. In fact, after this example, anytime we have a 0 in one of the rows or columns that we're expanding along, we're not even going to write this. We just know it's going to be 0 and we can forget about it. I'm back to a plus again. 2 times the 2 by 2 determinant I get from deleting this row, this column. That would be 2, negative 4, 0, 2. 2, negative 4, 0, 2. Okay, what is this equal to? Well, this determinant is 0 times negative 5 minus 2 times 1, which is negative 2. So I have 1 times negative 2 here. Okay, that's going to be a 0, so we don't need to bother writing anything for that. And then here I have plus 2 times this determinant. 2 times 2 is 4. Negative 4 times 0 is 0, and so this becomes 4. And I get negative 2 plus 8, 6. Okay, so expanding along the third column, the determinant comes out to 6. Now let's expand along some row. Well, we saw here that these cofactor expansions can be very messy. There's a lot of steps involved, but the fact that we had a 0 in the column that we expanded along helped because it eliminated one of those terms. If I expand along a row or a column with a lot of zeros in it, it eliminates a lot of the work for me. So that's actually part of the strategy in deciding how to evaluate a determinant. Choose a row or a column that has lots of zeros in it. For example, the second row of this matrix has 2 zeros in it. That's going to save us a lot of time. Second row. Let's try evaluating along the second row. Okay, so remember, if my top row goes plus, minus, plus, then my second row is going to go minus, plus, minus. 2 is the only non-zero entry, and it's associated with a plus, so I do not change its sign. It stays a 2. And then if I delete the row and column that it appears in, then I get a 2 by 2 matrix with just these 4 corners here. That's 2, 1, 1, 2. Okay, so what is this equal to? Well, it's 2 times the determinant, 2 times 2, which is 4, 1 minus 1 times 1, which is 1, so 4 minus 1, that's 3, 2 times 3, and I get 6. Same answer, right? And that's what we were expecting to happen. That should always happen with any determinant. So for that reason, like we had said, if you have to evaluate a determinant of some square matrix, something larger than a 2 by 2, a good strategy is to look for a row or a column that has lots of zeros. Let's try and apply that in this next example. This time I want to evaluate a 4 by 4 determinant. So In order to do that, we want to select a row or a column with lots of zeros in it. Well, the first row has a ton of zeros in it, so that's kind of the obvious first choice. And remember, we always start in the 1, 1 position with a plus. So evaluating this, I'm going to have 2 times a 3 by 3 determinant that I get from deleting this row and this column. 1, 2, 5, 0, negative 4, 2, 1, 3, 8. Okay. Now, you can kind of see how once you get into the 4 by 4, 5 by 5, and so on cases, this cofactor expansion idea gets way more complicated. Because imagine if I didn't have a row with so many zeros in it. In fact, suppose I had no zeros at all in this matrix. Then expanding along any row or any column is going to give me 4 different 3 by 3 determinants that I have to evaluate. And up here, we had to put this much work into evaluating a 3 by 3 determinant. We would have had to do that 4 times total to get this guy. So that's time consuming. And in fact, in the next section, we're going to talk about another method to help cut down on the amount of time that it takes to do a determinant like that. But lucky for us, we do have some zeros that we can utilize here. So now let's see if we can evaluate this. 2 times, okay, in order to evaluate this determinant, I need to expand along a row or a column, and I do have a column with a 0 in it, so let me expand along that column. I also like that there's 1s here. That makes things easier, a little easier also. So, okay, so if I expand along this row, that's plus, minus, plus. I'm going to have 1 times the determinant, negative 4, 2, 3, 8. So that's going to be, oh, let's write it that way. Negative 4, 2, 3, 8. Minus 0 times a determinant, but it doesn't matter because it's just going to be 0. Plus 1 times the determinant, 2, 5, negative 4, 2. Okay, this is equal to 2 times, we can just forget about the 1s since that's not going to contribute anything. Negative 4 times 8, that's negative 32, minus 6, so that would be negative 38. Okay, and then here, plus 1 times, this is 2 times 2, so that's 4 minus negative 20. So 4 minus negative 20 would be plus 24. Okay, so this comes down to 2 times negative 14, and then 2 times negative 14 should be negative 28. Okay? So that should be our determinant in this case. All right, so again, look for rows of zeros or columns of zeros to utilize those zeros to your advantage. One last thing to cover, this is a fairly short section because we're just introducing the way that we calculate determinants, but we really like triangular matrices when it comes to determinants because the method for calculating the determinant of a triangular matrix is extremely straightforward. Here's an example. This is straight out of your book. And we do state this as a theorem, but we're not going to prove it formally because it's easy enough to see why it's true with an example. The determinant of any triangular matrix is always going to be the product of its main diagonal entries. And to see why, take this 4 by 4 case right here. If I expand along this first row, because there's 3 zeros here, the only cofactor I need to worry about, and the expansion of this thing looks like A11 times this 3 by 3 cofactor here, this 3 by 3 determinant. Okay, here's that 3 by 3 determinant. But then if I continue expanding along this first row, again, I'm utilizing all of those zeros. So it becomes A22 times this 2 by 2 determinant right here. And you can kind of see how repeating that that expansion along the first row, each time this determinant shrinks down, we simply get the product of those entries that would have been on the main diagonal. So that's a huge time saver if you're able to work with a matrix that's triangular. Notice diagonal matrices being triangular as well would follow that same procedure. So later on in the course, we're going to talk about diagonalization of a matrix, something I've hinted at before, which takes a matrix that's not necessarily diagonal, but represents it as a product of very special matrices, one of which is diagonal, and that can make the calculation of a determinant much faster. That's chapter 5, so it's still kind of a ways off before we get there. Okay, but that's going to wrap it up for section 2.1.